Okay, so if your sign chart is describing the first derivative, okay, your first derivative, remember that x-axis, those are your inputs. So if there's a certain input here we're focusing on, if we're focusing on x equals c, so when I look down here, it's x is this number, it's c, okay? Then there's a couple of things that can happen here. Either when you put c into the function, it could be 0, or when you put c into the function, sorry, the derivative of the function, it can be undefined. And we're going to look at how that changes the shape of the graph. If at that specific input I'm looking at, if the derivative is 0, what will the graph look like? If that derivative is undefined, what will that graph look like? But one thing is for sure, if the graph has a negative slope to the left of whatever's happening there and a positive slope to the right, that means my tangent lines were pointing down. And then something happens here, we're not sure yet, and then my tangent lines go back up. If that happens, you for sure have a local minimum. At that point, x equals c. At that input, there'll be a local minimum. We're just not quite sure how the graph will look, depending on whether the slope is 0 or undefined. And likewise, if x equals c, and you put c into the function and the derivative of the function, and it's either 0 or undefined, again, we don't know which one. But if your tangent lines go from positive slopes to negative slopes, so if your slopes are going positive and then something happens and then they go negative again, whatever's happening there, it's still going to be what we call a local maximum. So we're going to see these 4 different cases with 4 different sign charts, and we're going to think about local mins and local maxes. So let's start here on 4. Okay, so we're being asked to create a sign chart for the first derivative, and then I threw in there the second derivative also. Just to remind us what, kind of refresh from last week what the second derivative is telling us. But let's do the first derivative first. So I'm going to create a sign chart. So I'm going to draw an x-axis, and then above the axis I do f prime of x. The important points to put on the sign chart are your critical values. So remember that critical value is some x value where your derivative is either going to be undefined, and we haven't really talked about that case yet. We didn't do that last week. Or it could be 0. Yeah, and where would our derivative, so what would be a critical point here? Oh, can y'all not see? Oh, you can't see, sorry. I have to reshare. There we go. Oh, yay, we can see it now. Okay. So what would be a critical value on that first graph there that we changed to number 4? Someone can drop one in the chat. What would be a critical value? Remember, the critical value is the derivative hits either 0 or 3. There you go, x equals 3. Perfect. So here, when x equals 3, up here on my graph, at x equals 3, if I put 3 into the function, it's a height of 5. But if I put 3 into the derivative, it's going to be 0 because there's that horizontal tangent line. So I'd say when x equals 3. Now, I like to write out when x equals 3, but MyMathLab is just going to put a 3 there because it's assumed to be an x value. And then I like to write out when I put a 3 into the function, I get a 0. But on your homework tonight, all you're going to see is just a 0 above that. So I'm going to try to write it like your textbook does, just so you can get used to that. Okay. And then all I have to do is describe my tangent lines. So to the left would match this part of my graph. And see how if I pick any point on that graph, my tangent line would be pointing up. So I'd have positive first derivatives. Okay. And then on the other side of my chart, that's going to correspond to this side. Now, remember, it might be a little misleading there. When I shaded my number line pink to the left of green, I'm really shading these inputs. That's what I'm really doing. This number line is corresponding to those inputs. But above the number line, I'm describing this part of the graph. I'm describing f of x. Remember, f of x is always your outputs. Or in this case, f prime of x. I'm describing the tangent lines of the graph. So that's why I highlighted the graph. And same thing on the other side. I'm technically looking at these inputs, but I'm describing what's happening to the graph. So that's why I highlighted the graph. And I can see that anywhere in that green region, if I pick a point, the tangent line will be pointing down. So it would be negative there. So that's what my first derivative sine chart will be. So later, if I give you this first derivative sine chart, you'll be able to kind of sketch out a graph that would be that shape. And what kind of point do we have on here? We're supposed to identify any local extrema. Local extrema. So where is our local max up here, right? This is going to be a local max. So it's a local max of 5 when x equals 3. So the actual local max is the highest output, but it's happening when the x is a 3. And I could see that from my sine chart. So if I didn't have that graph, if I covered the graph up with my hand, so if I didn't have this graph, just from the sine chart, I could see I was going up. I hit 0, so I went horizontal for a second, and I went down. I can get that shape just from the sine chart. So show me a status. How are you feeling on that sine chart right there? Okay, feeling good at that sine chart. Okay, then let's look at the second derivative sine chart. Remember, the second derivative describes the shape of the graph. Okay, so let's go ahead and do the second derivative. So if I want to do a second derivative sine chart, what shape is this graph? Let's see, this graph is the entire time, it's U-shaped and it's pointing down everywhere. So the entire graph is going to be concave down everywhere. There's not a point where it changes shape from concave down to concave up. So the second derivative sine chart, I wouldn't have any partition numbers on my number line. It's just going to be negative everywhere. It wouldn't matter what input I picked. If I plugged it into the second derivative, it'd be negative because the shape of the graph is concave down everywhere. Never changes. Okay, so let's go ahead and look at the sine chart here for number 5. So now we're going to do our first derivative sine chart. Okay. Now this one's a little different. We hadn't talked about this case last week, but I can see something weird is happening here again when x equals 3, right? When x equals 3, so that's going to be a partition number. And you have to think back, way back to test 1. Way back to test 1, where if you have a sharp point, the derivative does not exist. Because if you tried to draw a tangent line there, see how the tangent line could like teeter-totter on that sharp point? So we wouldn't have a definitive tangent line. It would rock back and forth on the point. So at this sharp point, that sharp point, if I put 3 into the function, I'd get a height of 1. But if I put 3 into the derivative, that would be an undefined derivative or does not exist. One of those right there. So above my 3, I think your book does UND for undefined. That's all they're going to put there. And then we're going to describe what's happening on the left of that and the right of that, the tangent lines. Okay, so let's go ahead and look at this. So to the left, for any of these inputs right here, I look at the graph, see how any point I pick will have a negative tangent line. And then on the other side, to the right, any of these inputs, boom, positive. Oh, I heard a little chime. Okay, there's a question in the chat. Is this when you can have either a critical value or partition number, but not both? No, James, that happens when you get a partition number that's not in the domain of the function. But when it comes to just being given a function and you having to graph it, I'm always going to give you polynomials. So you won't have to worry about it. When this was a 4-credit-hour course, we do rationals and logs and all kinds of things. So you'd have to worry about that special case. So your book mentions it and you might see it in the help tools, but it's not really going to apply to you because the domain of a polynomial will be all real functions. Now, if I just give you sine charts, I can give you some pretty wonky sine charts, but you'll just be told the derivative's undefined. You wouldn't have to figure that out on your own. Did that answer the question, James? Or yeah, it's if I can give you some really wonky sine charts. So if I give you some sine charts, you might have to create a graph that's very unusual, that might be a rational graph or a log graph or something weird. But when you're having to do it from scratch, I'll only give you a polynomial. So deep breaths. Oh, and I'm glad you said that, because I know some of y'all have been watching the lecture videos that come with a textbook. So in this section, they're going to do a lot more types of functions that I'm requiring of you. So it might not be the best idea for this section. Or to randomly pick problems out of the ebook to like practice. Make sure if you have any questions, you can just email me and I can tell you if it's one we actually cover in here. Okay, yeah, so this one, let's see, it went from negative tangent lines to positive tangent lines. Cool. And again, it's a sharp point, but that's still going to be a local min. Even though the derivative is not defined there, the function is. There's not a hole in the graph, right? So there's still going to be a local min here. And I can see it fits my definition of the first derivative going from negative. Then something weird happened, but then it went positive again. And since it's undefined, I know it's going to be that sharp point. I'm going to be able to see that from the chart there. So this is still going to be a local, this is going to be a local min of 1 when x equals 3. Let's do the second derivative now. What would our second derivative look like? Now this one's weird. So I see this shape graph over here. It's very subtle, but if I continued that, it kind of, see how it's leveling off a little bit? See how that's could potentially be part of a downward U-shaped graph? So this side's going to be concave down, and same thing on the other side. It's very subtle, but it's kind of curving. So if we did extend it, we could think maybe if I extended it, it would continue to be like subtly leveling off like that. So this is also going to be concave down. So the entire graph is going to be, this entire sign chart is going to be negative. But since the first derivative is undefined at 3, the second derivative is also undefined, right? Because the second derivative is the derivative of the first derivative. And if the first derivative is undefined, then you can't take the derivative of it. So your sign chart would look like this. It'd be negative everywhere. It's concave down on the whole graph. It's just they would make a note that at 3, if the first derivative didn't exist, then the second derivative can't exist. So that's what these sign charts would look like. So later, if I gave you these sign charts and you did not have this graph, from that information, you'll train yourself to be able to draw a sketch of this graph. It might not be perfect, but you'll know the general shape. You'll know there's a sharp point. You'll know it's concave down, curved on both sides. You'll be able to go from those sign charts to the graph. So how are you feeling on that one? Show me a status. Oh, we got some shocked faces and unsure faces. Yeah, once we start throwing in some sharp points and things, it gets a little bit more interesting. Trinity, go ahead.
So, what I'm confused about is whenever we're taking the second derivative, why is it all negative again?
The second derivative tells us the shape of the original graph. So the second derivative tells us concavity. So maybe let me, I'm going to write that down. Hold on. So the original function, that just tells us points on the graph. Points on graph. Right? That just tells us x, y ordered pairs. The first derivative tells us the slopes of the tangent lines of the graph, right? So slopes of tangent lines on f of x graph. But the second derivative is going to tell us the shape or the concavity of the f of x graph. So the shape, that downward opening U shape, that curve, upside down U kind of curve, even though it's in pieces there, that's called concave down. And that's how I knew that for this graph on 5, for this f of x graph, it was upside down U on the left and an upside down U on the right. It was just really subtle. So the concavity was concave down on the left and concave down on the right. And we'll...
I see. Thank you.
You're good? Okay, cool. Go ahead. Let's see. Patrick, go ahead.
What makes it undefined? I'm sorry.
Oh, no, it's okay. So that we have to reach all the way back to test 1. So a derivative is undefined in 2 cases, and we've just talked about one here. If there's a sharp point, we say the derivative is undefined because derivatives are slopes of tangent lines, right? And if I try to draw a tangent line here, think about it. It's kind of easier to see if the sharp point's the other way, but the tangent line would teeter-totter on that sharp point. It wouldn't be like one definitive tangent line. It would rock back and forth like a teeter-totter. So if you don't have one definitive tangent line, you don't have a slope on that sharp point there. So we just say it's undefined, or you can say does not exist. I think your book, I want to say does not exist, but I think your book says undefined. Did that help, Patrick?
Yeah, I don't remember that. I just forgot how it worked.
No, that's a good question. Thank you for asking. And then I think there was something in the chat. Yes, Marcus, this is being recorded. I don't want to jinx us, but right now it is being recorded. And I will save my changes. In fact, let me save right now. I'm going to save as I go so I don't do something silly. Okay, so let's see another case of this undefined slope, because I know that was tricky for us back on test 1, and we kind of glazed over it a little bit. So let's look at 6 and 7. These are other shapes of graphs we could have here. Okay, so let's do our sign chart. I'm going to draw my number line for X. Okay. So what in the world is happening on this one? Something weird is happening at 3. I'm just going to tell you again at 3. Something weird is happening. So let's just take a little journey. I'm telling you something weird's happening here. Let's take a little journey with our tangent lines and see what's happening. So let's look to the left. Let's look at these inputs here. So I'm going to follow this graph up here. Okay. So if I pick any point, it's my tangent line's pointing down, right? It's pointing down. So these are going to be negative. These are going to be negative. Okay. And then it's pointing down, and then boom, it goes vertical. So think back to algebra. What's the slope of a vertical line? Think back to algebra. Any ideas? Slope of a vertical line. Is it 0? No. Yeah, it's undefined. That's right. It's undefined. If you try to do slope formula, so I'm just going to draw a line with 2 points. If I try to do my slope formula with a rise over a run, when I try to do that, I would calculate, some number for my rise. I don't know, let's say 1, 2, 3 or something like that, down 3. But I would run 0. I wouldn't go left or right. And anytime you divide by 0, it's undefined. So if your tangent line goes vertical for even a split second, your slope is going to be undefined there. So the derivative is going to be undefined there. And then on the other side, once I pass through that point, for these inputs over here, for the other input, see how it's still, the tangent lines just go back, they're still negative, and then they're kind of tapering off. So since there isn't a sign change on my derivative from positive to negative or negative to positive, there's no local extrema. You have to have a sign change on that derivative sign chart for there to be a local extrema. There's not. But if I looked at this sign chart and I wasn't given this graph, and I said, oh, the tangent lines are going negative, it goes undefined and negative, I'll have to know, oh, that's not a sharp point. If I'm going negative and then undefined, it has to go vertical. I only have 2 choices, vertical for a split second or a sharp point, right? Well, if it was a sharp point, it'd have to go back up, which is positive, but it's not. So it has to be that vertical case, and then it goes negative again. So you can see that shape built into the sign chart. Okay, so let's look at the second derivative now. I'm going to be quiet for a second and let you try the second derivative sign chart and then see what you get, okay? Okay, let's see how you did on this one. Well, first of all, if the first derivative is undefined at 3, then the second derivative is also going to be undefined at 3, because the second derivative is the derivative of the first derivative. So that I know for sure. And then let's just look at the shape of our graph. Remember, this is going to describe the shape or the concavity of the f of x graph, which we were given up here. So this first part right here, it's very subtle, but it's a, it's a downward U. That's a downward shaping U. So this is going to be concave down here. We're going to go concave down. So if this area is concave down, that means my second derivative is negative. Anytime you have a negative second derivative, that's indicating concave down. But then on the other side, what happens? On this side right here, it changes. See how now it looks like a U-shaped graph? Part of a U-shaped graph going up. This is concave up, but they just did part of it. They did this part right here. So this is going to change to concave up. So that would be a positive second derivative. Anytime you have a positive second derivative, your graph shape changes to concave up. So the key to this section is being super organized and starting fresh with your thinking. See how on my first derivative sign chart, it was all negative, but my second derivative sign chart had some parts negative, some parts positive. Start fresh with every sign chart. And think about, okay, what is second derivative telling me about that f of x graph? It's telling me shape, so just focus on the shape. What is first derivative telling me? It's telling me tangent lines, so focus just on tangent lines. Okay? So show me a status. How are you feeling on that second derivative sign chart? Give me a happy face if you got it right so I can see how we were doing on that one. Okay, if you got it wrong, that's okay, because our brain is hardwired to learn from mistakes. That's one of the beauties of being a human. We can learn from our mistakes as long as you convince yourself why whatever you originally thought was wrong. Because what you wrote down, if you wrote something down that's wrong, your brain thought it was right. So you have to convince your brain that that was not right for it to absorb the right way to do it, okay? And sometimes you can do that just by seeing an example, and sometimes you have to talk that out. Something made sense in your brain that wasn't correct. So math is a language. Talking out in office hours or with Madhavi, our instructional associate, or with a tutor, like talking that out. And this type of stuff, y'all, this section is not business related. So any Learning Lab tutor should be able to help you. This is a pretty universal calculus topic. It's not business specific. Okay, let's do one more here before we try to get sign charts and go to a graph. Okay, let's look at this one. Let's do our first derivative sign chart. Okay, again, when x equals 3, something weird's happening. So let's look at this. I'm going to take a little journey with my tangent lines again. Let's do our little journey here. Let's look at the left. So from here, I'm looking up here at this part of the graph. Okay, so if I pick a tangent line, it's pointing down. Pick a point, the tangent line's pointing down. Then it's kind of leveling off, right? And then it's going to go 0. It goes horizontal for a split second. If it goes horizontal, the derivative is going to be 0. So if I put 3 into the original function, it has a height of 3. If I put 3 into the derivative, it would be a 0 because it went horizontal for a split second. So I'm going to go negative, negative, negative. Going to hit 0. And then when I look on the other side, here, it's continuing to be negative. My tangent lines are just staying negative. So see how similar these sign charts look? They have the same tangent line shapes, except for that one point, the vertical versus horizontal. Vertical versus horizontal. I'm going to come back up here to the number 6 graph, and I'm going to say when f was 3, if I put 3 into the when x was 3, if I put it into the original function, it had a height of 3. But if I put it into the derivative, it was undefined. All right? And that's my clue. Oh, it went vertical. Okay. Let's do that second derivative sign chart. If the first derivative is 0, what's the derivative of 0? 0, right? So if the first derivative is 0 and I take the derivative of 0, it's just a constant, so I'm going to get 0. So again, on my sign chart, at 3, if the first derivative is 0, the second derivative is 0. Okay. And let's look at the shape of our graph here. Well, on this side here, that's a concave up shape. So my second derivative would be positive. It's hard to see. Then on the other side over here, it switches. Now it's a U-shaped graph pointing down, so that's going to be concave down. So these are going to be negative. I know you might not think it now, but this actually turns out to be fun eventually at some point. Maybe not in the same semester you're taking it, but it's fun. I don't know. Or if you lie to yourself long enough, you start to believe it. So you can just tell yourself you're having fun. How are we feeling on this sign chart? Show me a status. Okay. Cool. Awesome. Okay, we're going to kick it up a notch. Here we go. Okay, at the top of the next page, I just, oh, that came out pretty blurry. I just cut and pasted something from your textbook with the different types of first derivative sign charts. And the top row, the derivatives are all zeros. And on the bottom row, they're all undefined. Oh, it uses ND for not defined, not UND. But I just put those there just for reference, since I know you don't have a paper textbook, you have the ebook, and it's hard to look things up. So I just copied and pasted that for you. Just different. So when you're stuck on a shape later, you'd be like, what are my possibilities? These are all your possible shapes here. Okay, so let's take a look at this problem. Normally, I would let you try this if we were face-to-face, and I use a document camera, and then I put people's graphs up and see what they look like, and are they matching, and all kinds of fun things. But we don't have the luxury of time here. So yeah, let's take a look at this. What information are we being given? And we're just being asked to sketch, so it's not going to be perfect. But we're given a table up here, and this table is giving us information about f of x. Remember, f of x, that's just telling you points on the graph. On the graph of f of x. So this is just a table of points. So let's just plot those points real quick. So this is the point -4, 0. So we'll just plot that. -2, -2, and so on. Okay, so those points kind of give us an idea of kind of what the graph looks like, but we need to connect the dots. Should we be connecting them with concave up curves, concave down curves, sharp points, verticals, horizontals? We don't know how to connect them. We need more information, but we're given more information in these sign charts, right? So I'm going to come over here And remind myself, the f of x sign chart is going to tell me things about the slopes of tangent lines of f of x. And it also tells me things about local extrema, right? Remember, from the f prime sign chart, again, that's kind of blurry, apologize. But this is going to tell us things also about local extrema. So, and local extrema. And then the second derivative sign chart is going to tell us about concavity of the original graph. Okay, so we got to put all this information together to get a sketch here. So let's look at our first derivative sign chart. Let's focus in on that idea of local extrema. So just looking at this chart, I can see that my derivative hit 0 twice. So I'm going to go horizontal 2 different places. When x equals 2, I'm going to go horizontal. Oh, sorry, -2. When x equals -2, so over here, find that point right there. So let's draw a horizontal tangent line there. And maybe I should do it in a different color since it's not really part of our graph, right? Let's do that in red. And then same thing when x equals +2. One of those points is a local extrema and one of them is not. And since we were given points to plot, you can kind of see which one's the local extrema. It's going to be this one right here. There's going to be a local min at x equals -2 because I can see that my tangent lines are going negative. They hit 0 and then my tangent lines go positive after that. So I'm going to have a local min. Oh, and the height is also -2. That's not confusing at all. A local min of -2 at x equals -2. So when I put -2 into the original function, I get 0. But if I put -2 into the derivative, if I put -2 into the original function, I get -2. But if I put -2 into the derivative, I get 0 out. I heard a little chime. Give me 1 second. Oh, sorry. Cassandra has a question on number 7. I did not answer something. So let me come back up here. Yeah, that is correct, Cassandra. On number 7, there were no local extrema. Thank you. I didn't answer that. So there are no local extrema, no local max, no local min, because the sign chart for the first derivative stayed negative everywhere. It has to change sign from negative to positive or positive to negative for there to be a local extrema. Thank you. Cool. Awesome. Okay. So let's see. So there was a local min there. Okay. And over here, there's not, right? Because oh, it's positive. My tangent lines are positive, so they're going up. They're going to hit 0, and they're going to continue up. So this is not a local extrema. Okay. So that's the main information I'm going to get from that sign chart. Now we need to get information about the shape, because the shape is really going to be what connects this graph together. So let's look at the shape here. So on my second derivative chart, I'm going to go from concave up to concave down to concave up again. And remember, those points where concavity changes are called inflection points. So I'm going to label these inflection points here just to practice that vocabulary. So At -1, I went from concave up to concave down, so that's an inflection point. So -1 over here, this is going to be an inflection point. And same thing when x is 2, that's changing shape. So that's an inflection point. Very subtle sometimes. Okay, so let's see. And y'all, when you draw these graphs, try to exaggerate the heck out of it. And if not, label concave up, concave down, because it can be so subtle. And that if you draw straight lines, I won't be able to give you credit. Like, it has to either be really obviously drawn or very obviously labeled. So what do I mean by that? I'm going to draw the graph and then explain. So it's concave up until I hit -1. So all this region is concave up. At -1, if I look up here on my sign chart, -1 is in this region. My tangent lines are still going up. So it's not going vertical or horizontal or anything there. It's just going to continue subtly going up. So I know it's going to be a diagonal going through there. It's not going to go vertical or horizontal. And it's going to be concave up. So, oh, here I'm saying like draw nicely. Let me try. I don't know. I'm trying to make it really obvious. That was concave up. Well, so much for being super obvious. But let's label that. Maybe it'll help. I want to get my full credit, right? So I'm going to label all of this concave up. Okay, concave up. Then it needs to switch to concave down. All this region is between -1 and 2 is going to be concave down. And I'm going to come look over here at 2. Oops. At 2, it did go horizontal. Oh, at 2, it did go horizontal. So I know it's going to go horizontal here. So I'm going to just like super over exaggerate that it went horizontal there for a split second. It's only supposed to be horizontal for a split second. I drew like a centimeter long, but that's just to exaggerate that went horizontal. And it's supposed to be concave down. So I'm going to try to connect those with like a subtle, downward U shape. I don't know. Easier said than done. So let me just write on there that that's concave down just to emphasize all this is concave down. Okay, and then I'm going to switch back concave up after that. So let's go ahead and do that. All this is concave. So everywhere else is concave up. So forever and ever concave up. So I'm going to try to draw that. So it was horizontal and then up. All that is concave up. Okay, this is a little bit fun, right? Or no? Am I the only one who thinks this is fun? Okay. Let me pause here and see if you have any questions on what just happened. So show me a status or ask a question. The happy faces are fewer and far between this time. Let me just recap what... Oh, go, Trinity, go ahead. Go ahead, Trinity.
So I think I got confused whenever -1, like you started like pointing -1 to f of x. Like what was that showing again? I don't.
No, that's okay. I was just trying to emphasize there that at -1, when I looked at that and I came up here to my graph, see how this is describing the tangent line? So the tangent line should, it points up. I wanted to emphasize it's not vertical or horizontal there. So I wouldn't make a horizontal graph. I wouldn't make a vertical graph. That's the tempting one to do, right? When you're going from concave up to concave down, it's really tempting to go vertical for a split second. But because in that region, my tangent line needed to be pointing up, it had to be slanted, I had to really emphasize that that's not vertical or horizontal. So let me put here, this is not vertical. Because if I put -1 into the first derivative, it would be a positive number. It wouldn't be undefined, or it wouldn't be 0. I was just trying to make that connection. And it's a subtle connection, so if you label your graph really well, it wouldn't matter. But maybe I should label that those were our inflection points there. Just to get every point I can on a graph if my sketch is messy, right? Like there was an inflection point when x was -1. There was an inflection point when x was a 2. And maybe, it might be good practice. Let's write this out. Maybe this will help. Let's talk about what's happening at -1. What if I put -1 into the original function? If I put -1 into the original function, what comes out? Well, I come back up here to my table for the original function, right? If I put -1 into the original function, a height of -1 comes out. If I put -1 into my first derivative, I'm going to look at the second table. -1 is in this region between -2 and +2. -1 is in there. So I don't know what the number is, but it should come out to be positive. So I should have an upward sloping tangent line. And then if I put -1 in the second derivative, I'm going to come look at this table, and it's telling me there's a 0 above the -1 on that table, so I know that derivative would be 0. And if the second derivative is 0, that's an inflection point. There's a chance the concavity could change there. It might not. But the only way concavity can go from negative to positive, from down to up, is to hit 0. The only way you can cross from a negative to a positive or a positive to a negative is to cross over 0. 0 is like a boundary line. So the fact that I went from concave up to concave down there, that can only happen if I hit 0 at that point. I don't know if that helped. Let me see. I have a little time. Did that help, Trinity? No?
Okay.
Okay, there's a couple of stuff going on in the chat. So Trinity, maybe when we do some more of these, it'll start to connect. I just want to remind everyone that I wish all the learning happened in this class. I wish I could take credit for all of your learning. 90% of the learning happens outside of class. Like, I do my best to lay a foundation to get you started, but I only see you for an hour, 20 minutes twice a week. You cannot learn calculus in an hour, 20 minutes twice a week. It takes a lot of time and energy. So, and I know the feeling you have right now, Trinity, is like uncomfortable because you don't you don't have to 100% understand everything right now. But when you go rewatch the video, look at the notes again. If it's not clicking, definitely reach out to me. Like, some of these ideas need a lot of time to sink in. You're not going to get it the first time you hear it or the first time you see it. And you have to be super patient with yourself, okay? And let me read what's in the chat real quick.
Okay.
Because I got behind here. Oh, okay. It was already answered. Thanks, guys, for answering each other's questions. Nice. Okay, cool. That was algebra. So good algebra review there in the chat. Any other questions or comments before we navigate away from this one? Okay, let's see. What do we got coming up next here? Here's another one. This one's got a little bit more interesting here. So now you see some NDs on there. Those are some undefined slopes, undefined concavity. Oh, okay, let's see. Let's see what's going on. Okay, first things first. The first table just tells you points on the graph. So plot those. Okay, so we plotted those points. The first derivative is going to tell me about local extrema and slopes of tangent lines, right? But I'm going to put local extrema. That's the most important. And second derivative is going to tell me concavity. Okay, so let's label any local extrema first. Okay, so let's focus here on when x is 1. When x is 1, -1, I have a slope of 0. So here's that corresponding point right there. A slope of 0 is always a horizontal tangent line. So I'm going to come really emphasize this horizontal tangent line here. I'll do it in red. This is going to be a horizontal tangent line. So there'll be some point, horizontal tangent line. Okay, and then I can see my tangent lines were negative before that, hit 0, and went positive after that. So that is a local min. There's a local min at x equals -1. So I'm going to label this local min. Oh, and this one's kind of interesting just to write it out. If I put -1 in the function, the height was 0. If I put -1 into the derivative, it's also a 0. Wow, the way I wrote local min, the n looks like an unhappy face, like a frowny face. So I have to change that because let's make that not look like a frowny face. We need to stay positive in here. Okay, then let's look at this next point. Oh my gosh, what's happening here at 0? Indeed, that you have two choices for this. This is either going to be a sharp point or it's going to go vertical. Maybe I should write that down here. It's going to do one of those two things. I don't know which one yet. It's based on a lot of other information, right? So we're going to have to think big picture here. I'm going to move that down here actually. Okay, so let's think about that. Sharp point or vertical. Well, let's think about the tangent lines. My tangent lines were going up, and then my tangent lines are going down. So I have to hit a local max there somewhere, right? If my tangent lines are going up on the left and down on the right, even though I'm not sure what's happening in the middle yet, I know I have to have a local max. A local max is going to happen there. So when x equals 0, let me go locate that on my graph here. When x is 0, I was up here. That's going to be a local max. Well, if it's a local max, it can't go vertical because vertical implies you'd be going up, vertical, and continue up, or you would be going down, vertical, and continue down. So it can't be vertical. So I know it's not going to be vertical. That means there has to be a sharp point there. A peak at a local max has to be that sharp point. So this is going to be a sharp point. And this just takes practice. You have to do a lot of these to figure that out. That's going to be a sharp point there. And then it's going to hit 0. The derivative hits 0 one more time at x equals 2. So right here, I'm going to hit 0 again. Anytime your derivative hits 0, that is a horizontal tangent line. Anytime you hit 0, horizontal tangent line. So I know this is going to go horizontal. So I'm going to draw that in over here. Is it a local extrema? Look to the left and look to the right. To the left, it's negative. To the right, it's negative. Was there a sign change? No. So it's not a local extrema. So let me pause there and give y'all a second to take a breath or see if you have any questions on how I went through that sign chart and translated information to this graph here, just kind of getting my thoughts down. Or show me a status if you don't have a question. How are you feeling on identifying local maxes, identifying local mins based on the sign charts, the first derivative changing from positive to negative? And if you're not sure, you can write yourself a little note like, ask yourself a question. How do we know, or how do we see local extrema on the first derivative sign chart? And then answer that question while you're studying. That's where your study's like, how did she see that local extrema? How did she know that? Anyone want to answer in the chat or out loud? How did I know just by looking at the sign chart there were local extrema? What has to happen there? Oh, there we go. Belinda has the question right there. She says she's confused on how I identified the local max at the ND. So the way you see local extrema on a sign chart is there has to be a sign change from positive to negative. So I'm just going to draw down here real quick. If you have a local max, it doesn't matter if it's a sharp point or a roundy mountaintop. I think of these little mountaintops, right? This one happened to go vertical for splits or teeter-totter, but both of these are local maxes. And on both of these, the tangent lines changed from positive tangent lines to negative tangent lines, right? Same thing on this one. I went from positive tangent lines to negative tangent lines. So when I look back up there at the sign chart, see how to the left I had positive signs on the derivative, and then it changed to negative signs, positive to negative. Anytime you go from a positive sloping tangent line to a negative sloping tangent line, I know there's a local max. The shape will depend on the derivative at that exact point. If the derivative is horizontal at that point, then I know it's going to be flat, like a nice curve, smooth curve there. If the derivative was undefined at that point, or they're just using ND, not defined. If the derivative's not defined there, then I know it's going to be sharp, a sharp point, because it was the sign change happening. Cool. No, sharp peaks can definitely be local extrema. A very classic one from algebra that you see is the absolute value graph. Remember when you had like absolute value of x? The parent function, it was a V-shaped graph with that sharp point. That's like a really classic one. Luckily, we don't have to do absolute value graphs in this class, but that's in a STEM calculus class, you'd see absolute value a lot. So it's like one of your super, super classic ones. But yeah, the function's defined. It's just the derivative's not. That's okay, but the function's still defined there. The derivative at that point isn't. That's okay. Okay, any other questions before we try to connect these dots? Okay, let's connect the dots, guys. Let me erase this down here. Time to connect the dots. Okay. Oh my gosh. You got this. Okay, connecting the dots, concavity. So what in the world is going on with my shape? So I am going from second derivative being positive, that means concave, up. And then between 0 and 2, it's going to stay positive, so that's going to stay concave up. And then after 2, to the right of 2, it's going to go, the second derivative is negative, that means concave down. So I'm going to have to keep that in mind when I go to connect this. It's going to be concave up, concave down. And just heads up, the way they got this undefined at 0 is if when I look above it, see how if the first derivative was undefined, if I take the derivative of the undefined, it's undefined, So since the first derivative is undefined, its derivative, the second derivative, will be undefined. And same thing here. Oops, when I look at this point, if the first derivative is 0 when x is 2, then the derivative of that will also be 0. So that's how they got those numbers, just looking at above and saying, okay, here are the first derivatives. What are the derivatives of those numbers? That's how they got those things. Okay, here we go. But just heads up on that second derivative sign chart, that 0 and undefined doesn't tell you anything about the shape of the graph. You're just focusing on the concave up and the concave down. So let's go ahead and do that. Let's focus on those things. So let's look here at this concave up first. So from negative infinity to 0, all here. So let me, if I shaded this in, this entire region, everything in there would be concave up. So everything in here is going to be concave up. Then it's going to switch. Oh no, it's going to stay concave up. Then everything in there from between 0 and 2, so between 0 and 2, it's going to stay concave up. So everything in here is going to be concave up. Okay, and then from 2 onwards, so from 2 onwards on my x-axis, everywhere in there, the graph is going to be concave down. So all this region, any graph I draw on this green shaded region is going to be concave down. Concave down. Okay, so now I just got to connect these dots. So these 3 dots right here, that's my first region. They have to be connected with concave up. So I'm going to do that. Okay, concave up. And it's going to go to a sharp point, so I have to kind of make it a little obvious. And there's a local min, concave up. Okay. Now, these 2 dots here in the next region, those also have to be connected concave up. So let's go ahead and do that. And again, it's a sharp point. So I'm trying to emphasize that sharp point. And then it needs to go horizontal. So let me really emphasize that horizontal. Even though it just goes horizontal for a split second, I'm drawing like a centimeter long piece of graph there just to exaggerate that, hey, that went horizontal. Plus I labeled it horizontal. So if this was a test, the grader would look at this and be like, oh, this student knows it's horizontal there because they wrote it the word horizontal and they overemphasized, they exaggerated that it went horizontal for a split second. And I'm just going to connect these concave up, make sure it's a sharp point here, and then concave up there. So this was concave up, concave up. Okay, and those next 2 dots, I need to connect them concave down. So this dot and this dot, I'm going to connect those concave down. Okay. Concave down. Oh, okay. Concave down. So the table they gave me were points on the graph. I plotted the points. The f prime sign chart, first derivative, told me local extrema. I labeled that. The f double prime sign chart, the second derivative, told me concavity. That's how I'm going to connect the dots. And I put a ton of labeling on here to make it super obvious. Because if you draw a sloppy graph on the test and it's not labeled, I can't give you points. If you draw a sloppy graph on the test and you labeled horizontal and you labeled sharp point and you labeled local min and you labeled local max, I'll give you the benefit of the doubt. So make sure you just label the heck out of everything. And heads up, on this My Math Lab homework, if you haven't been doing it up to this point, I highly suggest printing out the homework and practice these graphs by hand before you, because I think there's a lot of multiple choice on this homework where you just pick out, oh, I need to activate the homework. Sorry, let me put that on my to-do list. activate part 2. I'll do that right after class. But there's going to be like multiple choice where you just click what graph matches. But on the paper test you take in class, you're going to have to draw this stuff out. So make sure you're practicing drawing it. Your test is not multiple choice, okay? How are we feeling on this graph? Go show me a status. How did the shading help see the regions that were concave up and concave down? Okay, just a handful of people. It's okay if you're not feeling comfortable yet. It's okay. You can rewatch this video as many times as you want. Deep breaths. Okay, we only have 10 minutes or 8 minutes of class left, so let me think real quick how I want to spin that. Because the next problem on here was the graphing strategy. That's where I give you just an equation, and you have to create the first derivative sign chart, and you have to create the second derivative sign chart, and then you have to use the sign charts to make the graph. That takes a long time. There will only be one of those on the test, so we cannot do that in 8 minutes, but we have 8 minutes. So this means we're going to eat into class time on Thursday, which is fine. I'll extend the homework due dates. Since I haven't activated the homework yet, that's not a problem. So let me write myself a note, extend. So this homework won't be due until next week. That gives you all weekend to work on it and get help. So extended to, and I think there's also a take-home quiz. So I'll extend all that to Tuesday, the due dates. But let me see if we might have time. Yeah, let's look at 11. We're going to skip down to 11 because 11, you're just given a graph. And we're going to create the sign charts, and we can totally do this. So skip over to 11. Okay, so let's take a look at this one. It says the derivative of a given function is graphed below. The derivative is graphed. The derivative is graphed. Use the graph of the derivative of f prime, that's this, use this graph to create a sign chart for f prime and for f double prime. And use the sign charts to sketch a possible graph. Okay, so up until now, the graphs you were given were the original function. So you read them differently. Now they've graphed the derivative. So here, let's just think a little bit. What degree function is this derivative? Like what exponent would I see if I knew the actual rule? If they had given me an equation, what type of graph is this? What type of polynomial? Yeah, it's an x squared. It's quadratic, right? So I don't know exactly the numbers, but it would be in this form somehow, right? It'd be quadratic. And we're supposed to sketch a possible graph of the original function. F of x is the original function. So I'm just going to get our brain thinking here. If the derivative has an exponent 2 is the highest degree, and we're dealing with a polynomial here because quadratics are polynomials, what degree would the original function be? What exponent would I expect to see on that original function? Think about reversing the power rule. Yeah, it'd be an x cubed. So I don't know exactly what this is, but if this graph had an x cubed in it, there might be some number out to the front. If it was an x cubed, when I take the derivative of that, wouldn't that drop it down 1 degree to be a square? So this original graph, I don't know exactly the details yet, but it's going to be cubic. Cubic graphs can look like this. Here, I won't even draw the x-axis because we don't know. There's a lot of ways cubic, this is the parent function for a cubic. A cubic can also look like this or like this. All of these are cubic functions. So just using our algebra knowledge, when I go to my final thing that I should be doing here is sketch a possible graph of the original function. When I go to do that, it should be cubic. I'm going to create these sign charts. I'm going to try to sketch a graph. If I'm not sketching something that's cubic, I messed up. So you got to keep that in mind. The idea of getting information off of this graph and onto the sign chart is tricky. And we can't do it in 3 minutes. So I'm going to stop here. We're going to pick up on these notes where we left off. What I have planned for Thursday is really, really short. And next week, I planned all next week for one section for some word problems. So luckily, we have a built-in review day. I'm going to do my best to keep the review day. If for some reason we have to eat into the review day because this is taking longer than planned, I would rather you have a good foundation, than rush through this and then y'all be lost on homework, right? So if I do eat into the review day, I'll create another one of those like quick checks like I did last time. Since we didn't have a review day, I made that kind of practice test. I'll do another one of those. But my goal is to keep our review day. I think we can do it. We're going to go slow at the beginning, lay a good foundation, and then everything else will fall into place. So that's all I have for today. We will never get out early again in the history of this class ever. But I'll hang around. We just can't do any of these problems in 3 minutes. So you're free to log off. Definitely start the homework that I'm going to release. That you should be able to do the first few problems where if you're given the sign charts, you can create a graph. Do all of those before Thursday. Practice those. If I give you sign charts, can you create the graph? And then we're weaning ourselves off those sign charts, okay?